UFER stands for Underground Footings Earth Return. The UFER ground is a concrete encased electrode. This type of grounding system utilizes the conductive properties of concrete and the reinforcing steel within it to create a reliable connection to the earth. It's a method recognized and permitted by electrical codes for grounding electrical systems. The National Electrical Code, specifically Section 250.66, addresses the requirements for grounding electrode conductors, which often include UFER grounds. The fundamental principle behind the UFER ground is to establish a low-impedance path to earth for fault currents, thereby facilitating the operation of overcurrent protection devices and minimizing the risk of electrical shock. To construct the UFER ground, a length of steel reinforcing bar, typically a minimum of 20 feet, is encased within a concrete footing or foundation. The reinforcing bar must be at least 1/2 inch in diameter to meet code requirements. This encased rebar serves as the grounding electrode. The concrete must be in direct contact with the earth. This direct contact allows the earth to act as the return path for any fault current. The connection between the electrical system's grounding electrode conductor and the UFER ground is made using approved methods such as exothermic welding or listed grounding clamps. The grounding electrode conductor is typically connected to the reinforcing bar before the concrete is poured. The concrete encasement provides several advantages. Firstly, it protects the steel reinforcing bar from corrosion. Secondly, it provides a large surface area for contact with the earth. Thirdly, the concrete helps to maintain a stable moisture content around the electrode, which enhances its conductivity. The effectiveness of a UFER ground can be influenced by several factors, including the composition of the concrete, the moisture content of the surrounding soil, and the size and configuration of the reinforcing steel. In areas with dry or rocky soil, a UFER ground may provide a more reliable grounding solution than traditional ground rods. This is because the concrete encasement helps to maintain a consistent level of moisture around the electrode. The National Electrical Code provides specific guidelines for the installation of UFER grounds. These guidelines cover the size and type of reinforcing steel, the depth of the concrete encasement, and the methods for connecting the grounding electrode conductor. It is important to follow these guidelines carefully to ensure that the UFER ground provides effective grounding protection. One important consideration is the location of the UFER ground. The reinforcing steel must be encased in concrete that is in direct contact with the earth. This typically means that the UFER ground should be located in the footing or foundation of the building. The reinforcing steel should also be located as close as possible to the bottom of the footing or foundation to maximize its contact with the earth. Another important consideration is the connection between the grounding electrode conductor and the reinforcing steel. This connection must be made using approved methods, such as exothermic welding or listed grounding clamps. The connection must also be protected from corrosion. This can be accomplished by coating the connection with a corrosion-resistant compound. The size of the grounding electrode conductor is also important. The grounding electrode conductor must be sized according to the requirements of the National Electrical Code. The size of the grounding electrode conductor depends on the size of the service entrance conductors. The National Electrical Code also requires that the UFER ground be supplemented by an additional grounding electrode, such as a ground rod or ground ring. This supplemental grounding electrode provides additional grounding protection in case the UFER ground fails. The National Electrical Code provides specific requirements for the installation of supplemental grounding electrodes. These requirements cover the size and type of grounding electrode, the depth of the grounding electrode, and the methods for connecting the grounding electrode conductor. It is important to follow these requirements carefully to ensure that the supplemental grounding electrode provides effective grounding protection. The UFER ground is a widely used and effective grounding method. It provides a reliable low-impedance path to earth for fault currents. It is also relatively easy to install and maintain. However, it is important to follow the requirements of the National Electrical Code to ensure that the UFER ground provides effective grounding protection. In summary, the UFER ground is a concrete encased electrode that is used to ground electrical systems. It is a reliable and effective grounding method that is recognized and permitted by electrical codes. To ensure that the UFER ground provides effective grounding protection, it is important to follow the requirements of the National Electrical Code. The installation of a UFER ground typically involves several key steps. Firstly, the electrician determines the appropriate location for the UFER ground, typically within the building's foundation or footings. Secondly, they ensure that the reinforcing steel within the concrete is of the correct size and length, meeting the minimum requirements specified in the electrical code. Thirdly, the electrician securely connects the grounding electrode conductor to the reinforcing steel using approved methods such as exothermic welding or listed grounding clamps. Fourthly, the concrete is poured around the reinforcing steel, ensuring that it is fully encased and in direct contact with the earth. Finally, the electrician verifies the integrity of the grounding connection and documents the installation for future reference. The selection of appropriate materials is crucial for the long-term performance and reliability of a UFER ground. The reinforcing steel must be of a type that is resistant to corrosion, as it will be exposed to moisture and chemicals within the concrete and surrounding soil. The grounding electrode conductor must be sized appropriately to handle the maximum fault current that could occur in the electrical system. The connectors used to join the grounding electrode conductor to the reinforcing steel must be listed for direct burial and resistant to corrosion. The concrete used to encase the reinforcing steel should be of a high-quality mix that is designed to provide long-term protection against moisture and chemical attack. Regular inspection and testing of UFER grounds is essential to ensure that they continue to provide effective grounding protection throughout the life of the electrical system. Visual inspections can identify any signs of corrosion or damage to the grounding connections or reinforcing steel. Ground resistance testing can verify that the UFER ground is providing a low impedance path to earth. If the ground resistance is found to be too high, corrective action may be necessary, such as adding supplemental grounding electrodes or repairing damaged connections. Proper maintenance of UFER grounds can help to prevent electrical hazards and ensure the safe and reliable operation of electrical equipment. The benefits of using a UFER ground compared to other grounding methods are numerous. Firstly, UFER grounds typically provide a lower impedance path to earth than traditional ground rods, resulting in better performance during fault conditions. Secondly, UFER grounds are less susceptible to variations in soil conditions such as moisture content and resistivity, which can affect the performance of ground rods. Thirdly, UFER grounds are less likely to be damaged by physical impact or vandalism, as they are encased within the concrete foundation of the building. Fourthly, UFER grounds can provide a more aesthetically pleasing grounding solution, as they are concealed within the concrete and do not require exposed ground rods or wires. Fifthly, UFER grounds can be a more cost-effective grounding solution in some cases, as they eliminate the need for separate ground rods and associated installation costs. The limitations of using a UFER ground compared to other grounding methods include: firstly, the installation of a UFER ground must be planned and coordinated during the construction of the building, as it is difficult to add a UFER ground after the foundation has been poured. Secondly, UFER grounds may not be suitable for all types of soil conditions, such as highly corrosive soils that can damage the reinforcing steel. Thirdly, UFER grounds may not be as effective in areas with very low rainfall or prolonged periods of drought, as the concrete can dry out and reduce the conductivity of the ground. Fourthly, UFER grounds can be more difficult to test and inspect than traditional ground rods, as the grounding connections are typically buried within the concrete. Fifthly, UFER grounds may not be recognized or permitted by all local electrical codes, so it is important to check with the local authorities before installing a UFER ground. The applications of UFER grounds in different types of buildings and structures are wide-ranging. In residential buildings, UFER grounds are commonly used to ground the electrical service entrance, providing a safe and reliable path for fault currents. In commercial buildings, UFER grounds are used to ground the electrical distribution system, as well as sensitive electronic equipment such as computers and servers. In industrial facilities, UFER grounds are used to ground heavy machinery and equipment, protecting workers from electrical shock hazards. In telecommunication facilities, UFER grounds are used to ground communication towers and antennas, minimizing interference and ensuring reliable signal transmission. In hospitals and healthcare facilities, UFER grounds are used to ground sensitive medical equipment, preventing electrical noise and ensuring accurate readings. The future trends in UFER grounding technology include, firstly, the development of new concrete mixes that are more conductive and resistant to corrosion, improving the performance and lifespan of UFER grounds. Secondly, the use of wireless monitoring systems to continuously monitor the ground resistance of UFER grounds, providing early warning of potential problems. Thirdly, the integration of UFER grounds with smart grid technologies, allowing for remote control and optimization of grounding systems. Fourthly, the development of standardized testing and inspection procedures for UFER grounds, ensuring consistent and reliable performance. Fifthly, the increased use of UFER grounds in sustainable building designs, as they provide a more environmentally friendly grounding solution than traditional ground rods. When connecting to existing grounding electrodes, there are several important considerations. Firstly, it is crucial to identify the type and condition of the existing grounding electrode. This may involve visual inspection, testing, or consulting with a qualified electrician. Secondly, the new grounding electrode must be compatible with the existing grounding electrode in terms of materials and electrical properties. Using dissimilar metals can lead to corrosion and reduce the effectiveness of the grounding system. Thirdly, the connection between the new and existing grounding electrodes must be made using approved methods such as exothermic welding or listed grounding clamps. The connection must be secure and corrosion resistant to ensure long-term reliability. Fourthly, the size of the grounding electrode conductor connecting the new and existing grounding electrodes must be adequate to handle the maximum fault current that could occur in the electrical system. The size of the grounding electrode conductor is typically determined by the size of the service entrance conductors. Fifthly, the grounding system must be tested after the new grounding electrode has been connected to verify that it meets the requirements of the electrical code. This may involve measuring the ground resistance or performing a ground fault loop impedance test. The importance of proper grounding in electrical safety cannot be overstated. Grounding provides a low impedance path for fault currents to return to the source, allowing overcurrent protection devices such as circuit breakers and fuses to quickly interrupt the flow of electricity. This helps to prevent electrical shock hazards, reduce the risk of fire, and protect electrical equipment from damage. A properly grounded electrical system also helps to minimize voltage fluctuations in electrical noise, improving the performance of sensitive electronic equipment. In addition, grounding provides a reference point for voltage measurements, ensuring accurate readings and reliable operation of electrical circuits. Neglecting proper grounding can have serious consequences, including electrical shock, fire, equipment damage, and even death. It is essential to consult with a qualified electrician to ensure that your electrical system is properly grounded and meets the requirements of the electrical code. Understanding the principles of grounding is essential for anyone working with electrical systems. Grounding is the process of connecting electrical equipment and circuits to the earth, providing a low impedance path for fault currents to return to the source. This helps to prevent electrical shock hazards, reduce the risk of fire, and protect electrical equipment from damage. The grounding system typically consists of a grounding electrode, such as a ground rod or UFER ground, a grounding electrode conductor, and equipment grounding conductors. The grounding electrode is connected to the earth, providing a reference point for voltage measurements. The grounding electrode conductor connects the grounding electrode to the service equipment, such as the main panel board. The equipment grounding conductors connect the non-current carrying metal parts of electrical equipment to the grounding system, providing a path for fault currents to return to the source. The effectiveness of a grounding system depends on several factors, including the type of grounding electrode, the size of the grounding electrode conductor, the quality of the grounding connections, and the soil conditions. It is important to follow the requirements of the electrical code when designing and installing a grounding system to ensure that it provides effective grounding protection. The different types of grounding systems include, firstly, a solidly grounded system, in which the neutral point of the electrical system is directly connected to the earth. This type of system is commonly used in residential and commercial buildings. Secondly, the impedance grounded system, in which the neutral point of the electrical system is connected to the earth through a resistor or inductor. This type of system is used in industrial facilities to limit the magnitude of ground fault currents. Thirdly, the ungrounded system, in which the neutral point of the electrical system is not connected to the earth. This type of system is used in critical applications where a momentary interruption of power cannot be tolerated. Each type of grounding system has its own advantages and disadvantages, and the selection of the appropriate type of grounding system depends on the specific application. The role of the grounding electrode conductor is to connect the grounding electrode to the service equipment. The grounding electrode conductor must be sized according to the requirements of the electrical code. The size of the grounding electrode conductor depends on the size of the service entrance conductors. The grounding electrode conductor must be made of copper or other corrosion-resistant material. The grounding electrode conductor must be installed in a manner that protects it from physical damage. The grounding electrode conductor must be connected to the grounding electrode and the service equipment using approved methods, such as exothermic welding or listed grounding clamps. The function of equipment grounding conductors is to connect the non-current carrying metal parts of electrical equipment to the grounding system. The equipment grounding conductors provide a path for fault currents to return to the source, allowing overcurrent protection devices to quickly interrupt the flow of electricity. The equipment grounding conductors must be sized according to the requirements of the electrical code. The size of the equipment grounding conductors depends on the size of the circuit conductors. The equipment grounding conductors must be made of copper or other corrosion-resistant material. The equipment grounding conductors must be installed in a manner that protects them from physical damage. The equipment grounding conductors must be connected to the electrical equipment and the grounding system using approved methods, such as screw-type terminals or listed grounding connectors. Understanding ground fault circuit interrupters and their operation is crucial for electrical safety. Ground fault circuit interrupters, commonly known as GFCIs, are devices that are designed to protect people from electrical shock hazards. GFCIs work by monitoring the current flowing in the hot and neutral conductors of an electrical circuit. If there is a difference of more than 5 mA between the current flowing in the hot and neutral conductors, the GFCI will trip, interrupting the flow of electricity. This difference in current indicates that some of the current is leaking to ground, which could be a sign of an electrical shock hazard. GFCIs are typically installed in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. GFCIs are required by the electrical code in these areas. GFCIs should be tested regularly to ensure that they are functioning properly. To test a GFCI, press the test button on the GFCI. The GFCI should trip, interrupting the flow of electricity. If the GFCI does not trip, it should be replaced immediately. Arc fault circuit interrupters and their function are also important to know about for electrical safety. Arc fault circuit interrupters, commonly known as UFERs, are devices that are designed to protect against electrical fires. UFERs work by monitoring the electrical circuit for the presence of arc faults. Arc faults are dangerous electrical discharges that can occur when electrical insulation is damaged or when electrical connections are loose. Arc faults can generate high temperatures, which can ignite nearby flammable materials. UFERs are typically installed in bedrooms and other areas where there is a high risk of electrical fires. UFERs are required by the electrical code in these areas. UFERs should be tested regularly to ensure that they are functioning properly. To test an UFER, press the test button on the UFER. The UFER should trip, interrupting the flow of electricity. If the UFER does not trip, it should be replaced immediately. Common grounding mistakes to avoid include, firstly, using undersized grounding conductors. The grounding conductors must be sized according to the requirements of the electrical code. Secondly, using improper grounding connections. The grounding connections must be made using approved methods. Thirdly, neglecting to ground non-current carrying metal parts of electrical equipment. All non-current carrying metal parts of electrical equipment must be grounded. Fourthly, failing to test the grounding system after it has been installed. The grounding system should be tested to ensure that it is functioning properly. Fifthly, modifying the grounding system without consulting a qualified electrician. The grounding system should only be modified by a qualified electrician. The long-term maintenance of grounding systems involves regular inspection and testing of the grounding system. The grounding connections should be inspected for corrosion and damage. The ground resistance should be tested to ensure that it is within acceptable limits. The grounding conductors should be inspected for physical damage. Any problems with the grounding system should be corrected immediately. The grounding system should be maintained in accordance with the manufacturer's instructions and the requirements of the electrical code. The process of troubleshooting grounding problems involves firstly, identifying the symptoms of the grounding problem. Secondly, inspecting the grounding system for any obvious problems. Thirdly, testing the grounding system to determine the location and cause of the problem. Fourthly, correcting the problem by repairing or replacing the damaged components. Fifthly, testing the grounding system after the problem has been corrected to ensure that it is functioning properly. Grounding and bonding are two distinct but related concepts in electrical safety. Grounding refers to the connection of electrical equipment and circuits to the earth, providing a low impedance path for fault currents to return to the source. Bonding refers to the connection of non-current carrying metal parts of electrical equipment to each other, creating an electrically conductive path that can safely carry fault currents. Grounding and bonding work together to provide a comprehensive electrical safety system. Grounding helps to prevent electrical shock hazards by providing a path for fault currents to return to the source, while bonding helps to ensure that all metal parts of electrical equipment are at the same electrical potential, reducing the risk of electrical shock if someone comes into contact with two different metal parts. The application of NEC Section 250 encompasses a wide range of requirements for grounding and bonding electrical systems. NEC Section 250 provides detailed guidelines for the selection and installation of grounding electrodes, grounding electrode conductors, equipment grounding conductors, and bonding jumpers. NEC Section 250 also covers the requirements for grounding and bonding specific types of equipment, such as transformers, generators, and motors. It is important to consult NEC Section 250 when designing and installing electrical systems to ensure that they meet the requirements for grounding and bonding. Grounding for sensitive electronic equipment requires special attention. Sensitive electronic equipment, such as computers, servers, and medical equipment, can be susceptible to damage from electrical noise and voltage fluctuations. Proper grounding can help to minimize electrical noise and voltage fluctuations, improving the performance and reliability of sensitive electronic equipment. Grounding for sensitive electronic equipment typically involves the use of isolated grounding systems, which provide a separate grounding path for the sensitive equipment. Isolated grounding systems help to prevent electrical noise from other equipment from interfering with the operation of the sensitive equipment. Understanding static electricity and its control is essential for electrical safety, especially in environments where sensitive electronic equipment is used. Static electricity is the buildup of electrical charge on the surface of an object. Static electricity can be generated by friction, induction, or other means. Static electricity can cause damage to electronic equipment, as well as create a risk of fire or explosion in certain environments. Static electricity can be controlled by grounding, bonding, and the use of static dissipative materials. Grounding provides a path for static electricity to discharge to the earth. Bonding helps to ensure that all metal parts of electrical equipment are at the same electrical potential, reducing the risk of static discharge if someone comes into contact with two different metal parts. Static dissipative materials are materials that allow static electricity to dissipate slowly, preventing the buildup of high static charges. Lightning protection systems and grounding are essential for protecting buildings and equipment from lightning strikes. Lightning strikes can cause severe damage to buildings and equipment, as well as create a risk of fire or explosion. Lightning protection systems are designed to intercept lightning strikes and safely conduct the lightning current to the earth. Lightning protection systems typically consist of lightning rods, conductors, and grounding electrodes. The lightning rods are installed on the roof of the building and are designed to intercept lightning strikes. The conductors connect the lightning rods to the grounding electrodes. The grounding electrodes are installed in the earth and provide a path for the lightning current to dissipate safely. Proper grounding is essential for the effective operation of a lightning protection system. The grounding electrodes must be sized and installed in accordance with the requirements of the electrical code.